So, good day to everyone. Today we will take a look onto the performance of DC generator. So, what we have on this test bench. First of all, here is the DC generator. Most probably the smallest one which is possible. It's only 350 watts of rated power, yeah. But for our laboratory needs it's fully sufficient. So this DC generator, this is only this part, yeah, only this part, because this is the holder, yeah, it's not a part of a generator, yeah. So this generator is driven by means of AC motor, yeah. And here is the driving shaft inside, yeah. So okay, the speed of AC motor can be controlled by means of AC drive. So I can adjust, here's the frequency, and therefore speed of AC motor will change, yeah. Okay. So this DC generator, of course, is air cooled. So as you can see, here is the cooling fan, yeah, centrifugal type. So it sucked air from the center, and then air escaped from these windows which are there, yeah. So air escaped from here. So as you can see, exactly this generator has no air which goes through the generator. However, typically it is done like the air goes through the generator, but in this case it is not so. Okay, so output, so you can attach and disattach. Of course, this is not a part of a generator, this is a handmade, yeah. And this output further is supplied to this test bench. So what we have on this test bench? First of all, measurement instruments. We can measure field current, load current, as well as output voltage. Also, I can enable or disable field current, and I can fully enable or disable load. Field current, which is measured here, can be controlled by means of this rheostat, yeah? So I can increase or reduce the field current. In a similar way, I can control load. So load is enabled here, and here is the load ampere meter. And load can be controlled by means of this rheostat. This is the minimum resistance because the rheostat is connected from this side here. So this is the minimum resistance, therefore maximum load, and vice versa. Here is the maximum resistance and minimum load. So also I have connected this multimeter because it's not easy to very precise to take measurements from this scale, so I have also connected this multimeter in order to see output voltage, yeah. Okay, so AC drive is powered from the wall socket, yeah, from here. And also, in order to operate, the generator should to have field current. So from where to take field current? In our case, we will play with the separately excited DC generator. It means that field winding, which is parallel, of course, and shunt, field winding is powered by some external DC source. In our case, we got field current from this circuit board, yeah. So here it is. DC, of course, we need DC. Here's the wires, and this goes here. Okay. So, what we will do today? On this test bench, we have armature winding, yeah, which is connected. Here is the output, yeah, two terminals outputs, and these outputs are connected to the output voltmeter here and also here. Further, through the ampere meter, this one, we can supply this output through this switch. We can supply this output to the load. Here is the load, yeah. We can also adjust field current by means of this rheostat, this one, yeah. And we can also know the field current, which is measured by means of this ampere meter. Also, we can adjust speed of a generator by means of changing frequency on the AC drive. Frequency here, yeah? So I can adjust. Now it is exactly 50 Hertz, so it is 3000 RPMs. So, let's check how output voltage depends on various parameters. At first, we can represent generator as a EMF source, which is in series with the internal resistance. Internal resistance of this generator is caused by the resistance of armature windings. And of course, by means of these wires, yeah, because wires also have some resistance. Okay. So, as you can see, EMF depends on speed and magnetic flux. Speed, it's very clear, yeah? This is the constant value. So speed, it's very clear. And what about the magnetic flux? Magnetic flux in the DC generator is generated by means of field current and by means of field winding. So, if I will control field current by means of this rheostat, then I will control magnetic flux. But the EMF by itself is directly proportional to the magnetic flux. So, by increasing field current, we will increase EMF, therefore we will increase output voltage. Output voltage and EMF. The difference is in voltage drop across internal resistance. Yeah? So, if I will operate at no load, if load current will not exist, then this will be equal to 0, and therefore I can say that output voltage would be equal to EMF. Because if there are no load current which flows here, yeah, then there are no current through the internal resistance, therefore no voltage drop, and therefore this voltage is equal to EMF, because here we have no voltage drop. So okay, at first let's check how output voltage yeah, depends on field current. Most probably by increasing field current we will increase magnetic field, so we will increase also EMF. So let's check. So let's start the drive. So now we got 3000 RPMs, yeah. Now I will enable field. And now I am able to control the field. Yeah. So now it could put it to the minimum possible. Yeah. But also in this case we got approximately 0.6, so I can adjust by means of this rheostat. Yeah. I will adjust it to 0.6. Okay. So 0.6 give us output voltage of 21 volts. Now I will increase field current. Okay. 0.8 give us output voltage of 25 volts. Okay, let's adjust it further. One ampere give us 29. 1.2 give us 31. So, as you can see, by means of adjusting field current, we can adjust output voltage. Yeah? And this relationship is almost proportional. If you will build a graph, you will see that you will got something like this. And further, graph starts to deflect slightly. This happens due to the fact that magnetic conductor of the machine, which is made of iron here, magnetic conductor of the machine will become saturated. So we continue to increase field current, but there are no increase in magnetic field. Yeah, and therefore voltage starts to deflect. However, this phenomena is not clearly seen from this data. We have to increase much more field current in order to see this phenomenon. Okay, so let's reduce voltage because it's slightly more than allowed for the generator. Let's set it to, say, 20 volts. So I reduce the field current in order to reduce the voltage. Slightly more, slightly less, yeah. Okay, so 20 volts. So now I will adjust the speed. So, at the speed of, now we have exactly 3050 Hertz, yeah. At the speed of 3000, we have voltage of 20 volts. Looking onto this formula, onto this equation, we can see that EMF is directly proportional to the speed. So, most probably, if I will reduce speed twice, then EMF also will drop twice. So I will put frequency to 25 Hertz. Okay, 25 Hertz. So now voltage is only 10 volts. So as you can see, EMF in the generator is directly proportional to the speed. Yeah. In a similar way, I can increase get 30 volts with the speed of 450, and in the same way we can increase even more and more. So let's slow down it because it's very noisy. Yeah. So as you can see, output voltage of a generator is directly proportional to the speed, which confirms these equations. Yeah, speed and output voltage through the EMF. Yeah. Okay. So now let's check how output voltage depends on load current. The idea is as following. EMF depends on speed and magnetic flux. So EMF depends on speed and field current. In this experiment, I will hold speed constant and I will hold field constant. Therefore, EMF will be also constant. However, output voltage, this is the EMF minus voltage drop across internal resistance. EMF voltage minus voltage drop across internal resistance. This is the output voltage, yeah, which is here. So, we will see how internal resistance impact onto the output voltage value. So, let's increase speed back. Okay. And let's adjust the field current to say 20 to get to 25 volts. So I increase the field current. Yeah, I increase the field current in order to get 25 volts. Okay. So now I have 25 volts at zero load. Now I'll switch the load on, so I get some load current, and now I will increase this load current. I will increase this load current to, for example, 4 amperes. Okay, so 4 amperes. The output voltage drops to 22.7. Now let's go to 8 amperes. Oops. Okay. Output voltage is 20.5. Maybe a little bit more. Let's say 12. Which is the maximum for this generator. So we got output voltage of 17.7. And I will reduce load because it starts to heat up. Yeah. Okay. So now, as you can see, the output voltage depends on load. If you will build the graph, you will see that this relationship is almost linear. First of all, we are at no load, or idle, yeah, no load current. So at no load we have 25. From this equation we can see that at no load, when this is equal to 0, yeah, this one is 0, so we got EMF. So we can also say that this is the EMF. Focus? Yeah, so this is the EMF. Further, EMF depends only on speed and magnetic flux. These has been not changed, yeah, because field current and speed was constant. So the EMF will remains unchanged. Where is the focus? Oh. However, output voltage starts to drop, and at 12 amps of load we got only 18 volts. So you will got such graph. Yeah, it's switched off. Okay. That's it, yeah. So if you will continue to increase load, the output current increases for more than allowed, because this is the maximum permitted current, yeah. And you will burn the generator, it will overheat. Yeah, so this is the problem. So this is the maximum voltage, maximum current which we can get from the generator, because otherwise it becomes too hot. However, there is only one problem with the generator. The problem is that we have to use some source of power in order to get filled. In our case, we got this power from this circuit board. On airplane, we do not have any standalone sources, and therefore we are not able to get field current from somewhere. So the idea of the airplane is to use self-excited generator. Yeah, in the self-excited generator we do not have any sources, and we take field from the generator output. Yeah, so field goes here. So now let's do this. So I will disable this supply and I will take supply from the output. Yeah, from the output we'll put this supply into the field. Okay. So I have to reset the AC drive. Okay. Back 50 Hertz, 3000 RPMs. Yeah. So now, no field, no output voltage, because no field, no EMF. However, in reality, we have slight voltage. We have, in this case, 1.5, in this example, 1.5 volts. This comes from the residual magnetism. The idea is that when the magnetic conductor has been magnetized once, then when I will remove magnetizing current, some residual magnetism still will exist. And this residual magnetism will produce very little EMF. In our case, this is the 1.5 volts. So, if I will build this graph, actually it will not go from the zero. In my case, it will go from the 1.5 volts. Okay. And this 1.5 volts is very significant. This will provide for us self-excitement. So now, I will put this 1.5 volts into the field. So 1.5 volt from here will apply to the field. Oh, very little, but it is here. So we got a little bit more voltage. Now let's reduce the resistance in the field, and we got higher field current. Yeah, I reduce it. Higher field current, and therefore output voltage also increases. So this is the self-excitement process. Yeah. Okay. Let's say 25 volts again. Yeah. No, in our previous example we have 25, so 25 again. The self-excitement process takes some time. Look. Yeah, it takes some time. Okay. So now let's again increase load. What we will get? At no load we have a little bit less, readjusting. At no load we have 25. 25, okay. So now let's increase load to 4 amperes. As you can see, output voltage is only 19 volts. 19 instead of 23. Where is the joke? The joke is here. When I start to increase load, the output voltage drops. But the output voltage is the source for the field. Therefore, field also will drop. However, if field drops, then output voltage drops even more. In this case, field will drop even more. Look onto this. I will remove the load. What will happen? Without load, voltage is higher and therefore field also is higher. With load, output voltage drops and therefore field drops and therefore output voltage drops even more. So, if we will continue to increase load current, at some position it will stop, and further the voltage is too low to hold field current, and therefore further output voltage drops to 0 and current also drops to approximately 0. But the field is equal to 0. This is the short circuit of the output of this generator. But the current is very low It's much more less than 12, which is the maximum for this generator. This happened because output voltage drops to 0, so the field drops, output voltage drops to 0, so the field also drops to 0. No field, no magnetic flux. Magnetic flux now comes only from the residual, so the EMF is very low, and therefore current also is very low. So that's it. If I will remove load, the self-excitement process will raise up the output voltage back. So, as you can see, self-excited generator is able to operate. However, its characteristic becomes much less stable, and you will got something like this, and further it will drop somewhere here. Of course, you are not able to operate here, and of course you are not able to operate here because this is the unstable operation, and you can use only this part of the characteristic. However, generator which is self-excited do not require any external sources to provide power for the field, and therefore this system is fully self-contained. Look, without load, field is enabled. Now I will switch on the drive, and you will see that output voltage will rise up automatically. Yeah, no problem. Oh.